Okay, I want to try one like number 10. And in the, I think number 10 is one of the ones where you're asked to use your calculator to help find the value of the approximation. So I'm going to do one very similar to it. We're going to find M4. M stands for the midpoints. We're going to be using the midpoints for the subintervals. The function I'm going to use is cosecant x. I think in number 10 it's secant x. And I'm going to go over the interval from 1 to 2 as opposed to 0 to 1 in number 10. So very similar. So the first job, as always with these, is to find your width of each subinterval, your delta x. And it's the length of the interval. So the interval is going from 1 to 2. So I do 2 minus 1. Length is 1 divided by 4, right, which is the number of subintervals. So this subscript 4 again indicates the number of subintervals. So 1/4 or 0.25. So I'm starting with x sub 0 is 1, and then I add 0.25. I get 1.25 for x of 1. 0.25 again is 1.5. 0.25 again is 1.75. 0.25 again is 2. And I should end up right with the right endpoint on our interval. So these are the dividing lines for our subintervals. I'll list our 4 subintervals here. So the first one goes from 1 to 1.25, 1.25 to 1.5, 1.5 to 1.75, 1.75 to 2. So those are our endpoints. Now, if I was doing L4, I'd be using the left endpoints. I'd be using 1, 1.25, 1.5, and 1.75 to find the heights of my 4 rectangles. If I'm doing the right-hand sums, if it was R4, I would be using 1.25, 1.5, 1.75, and 2. But I'm not using either of those. I'm doing midpoints. So I've got to compute the midpoints now. So it's just simply the average of the left and right endpoints for each subinterval. So I add 1 to 1.25, divide by 2, I get 1.125. So again, I'll add the 2 together and divide by 2, add the 2 together, divide by 2. And you could do that for each interval. Now here's a little trick. The difference between each of these midpoints is exactly equal to delta x. So when you find this first one here, if I just add 0.25 to 1.125, I get 1.375. So just add 0.25, add 0.25, add 0.25. Okay, so that gives you your midpoints. So now we're ready to go. We can find the value of M4. So let's add up the areas of the 4 rectangles. Their widths are all the same, delta x. The heights are going to be evaluated, right? The function evaluated at the midpoint. So the first midpoint, second midpoint, evaluate the function at that midpoint times the width, and so on. Okay, so this delta x is common to all 4. I'll go ahead and factor that out. And what is f of 1.125? Remember, our function f of x in my example is cosecant x. So this will be cosecant of 1.125. Factor out the delta x plus cosecant of 1.375, cosecant of 1.625, and so on. Okay, so so why did I say use your calculator? Well, here, I mean, what is the cosecant of 1.125? I don't know, right? I need the calculator to do that, right? That's where I have to use the calculator. Now, I don't have a cosecant button on my calculator. I only have a sine, cosine, and tangent. Does that mean I cannot do this problem? No. We recall that the cosecant of x is equal to 1 divided by sine of x. That's the reciprocal relationship between those two functions. So instead of doing cosecant x, I have to actually write in 1 divided by sine of x. And so I enter in this expression here in the calculator, and it looks like this in my calculator. Okay, so there's the delta x, remember, was 0.25, so that's the 0.25 times, and then in parentheses, right, I've got cosecant of 1.125, so that's 1 divided by sine of 1.125, plus cosecant 1.375 is 1 divided by sine of 1.375, and so on, right? So I have to do 1 divided by each time, okay? And then hit enter, and I get the value for M sub 4, which rounded off then is what I'm writing here. Now, keep in mind that you do need to be in radian mode. So anytime you're dealing with trig functions, so if you've been doing some work where you're using degrees, check your mode on your calculator and make sure that you are in radian mode. Make sure that's highlighted. Move your cursor down and highlight radian, not degree. you'll get an incorrect result. Now, graphically, if we took a look at this, I actually entered the function cosecant, which is again 1 divided by sine of x, and I graphed it on the interval from 0 to 3. You know, y is going from -1 to 3. I opened up a window to look at that graph, and you can see it's above the x-axis. Here's x equal 1, here's x equal 2. And so, you know, basically, if I sort of try and somewhat reproduce graphically what's going on there from 1 to 2, the function looks something like this, right, on the calculator, whatever that is. And so what we're doing is we're breaking up the interval from 1 to 2 into 4 equally spaced, right? So here's 1.25, 1.5, 1.75, 2. But we're using the midpoints, right? So the midpoints are going to be, you know, the 1.125, 1.375, and so on. So on this first interval, what's the height of our rectangle going to be? It's going to be the value of the function at, right, that value right there will be the height. So the length of this line segment is the height. And so our rectangle actually looks like that, right? And then, you know, and so on. So I'll just draw in the other rough estimates of these rectangles. So there would be the area where the M4 is the area of these 4 rectangles. Now what we're trying to approximate, of course, is the area under this cosecant function from 1 to 2, you know, which is just everything, including this part that's not in that rectangle, and, you know, all this stuff. And so, you know, you can see, looks like those areas are going to be pretty close to one another, right? So it's a pretty good approximation. Again, if I want to get a better approximation, I increase the number of subintervals, you know, from 4 to maybe 8 or 10 or 20 or 50 or 100. Of course, what we're getting to later on in the exercises, right, is to take an arbitrary number of subintervals n and then push n to infinity. But right now, again, notice with these problems, when you're just finding, you know, approximations for a fixed number, you know, in this case 4, be it midpoint, left endpoint, or right endpoint, you do it all the same, basically. You know, there's no summation notation. You don't need to do that. You just write it all out. And like in this case, if you need your calculator, that's what I mean by using the calculator to evaluate these expressions here. All right, hope that clarifies things for this one, and we'll do some more soon.